Welcome, dear students. We'll do the notes for section 5.4 today. It's a very long set of notes. We'll do it in 3 parts, and you can do some of the exercises at the end of each part if you prefer to do exercises rather than watch all the notes at once. Notation here that's really important. Usually when we have a function f of x, we write the antiderivative of f with a capital letter, capital F. What that means, fundamental theorem of calculus, is that the derivative of capital F is the function f of x. You can also write it like that, df dx equals f of x. The fundamental theorem of calculus comes into 2 parts. The second part is the explanation of how you compute definite integrals when you want to find areas. So basically you find the antiderivative capital F and then you plug in upper limit minus lower limit and it'll yield the area under the curve. We'll go to some examples of that immediately, and this starts actually at example 4. We'll come back later to examples 1, 2, and 3. So this is the example we used at the beginning of this chapter. We had a function and we were trying to evaluate the area under the curve between x equals 1 and x equals 5, and we did that with Riemann sums using rectangles. Now we can do it using integrals, so we are looking for the integral between x equals 1 and x equals 5 of the function f of x. What we need to do is to integrate, so this 1 over 8 is a factor. I can move it in front of the integral and just leave it there. All I need to do is to integrate negative x cubed plus 7x squared minus 11x plus 21. The integral is, you know that now, negative 1 over 4x to the 4th power plus 7 over 3x cubed minus 11 over 2x squared plus 21x. Now we use the second part of the fundamental theorem of calculus, so we're going to plug in 5 and we're going to do minus and plug in 1. So what happens is here the 1 over 8 is still there, negative 1 over 4, 5 to the power 4 plus 7 over 3, 5 cubed minus 11 over 2, 5 squared plus 21 times 5. If we evaluated this, we would find 12.86. Minus 1 over 8, and we put x equals 1 for x, and we get, when we evaluate, 2.20. So finally, 12.86 minus 2.20 yields us with the answer 10.667, which is the shaded area here. Example 5. This is the integral from 1 to 3 of x squared minus 3 root x plus 4. We have no idea what the graph looks like. It doesn't really matter. We're not asking for areas here. We're just calculating the definite integral. So the integral of x squared is 1/3 x cubed. The integral of negative 3 root x is 2x to the power of 3 over 2. And the integral of 4 is 4x. I'll plug in 3, which is 1/3 times 3 cubed minus 2 times 3 to the power of 3 over 2 plus 4 times 3, which gives me 10.61, minus, and same thing, but we plug in x equals 1 here, so minus 2.33 if you try with your calculator. The answer of this definite integral is 8.274. So an indefinite integral is when I don't have a lower limit and an upper limit. If a definite integral is when I have a lower limit and an upper limit. Example 6. The integral from 0 to 2 of the absolute value of 2x minus 1 dx. There are 2 ways of doing that. The really easy way is to use geometry and realize this function absolute value of 2x minus 1 is like this. So when I'm looking for the integral between 0 and 2, really what I'm doing is adding the area of the small triangle here and the bigger triangle there. This small triangle and that bigger triangle. So using base times height over 2, I can easily find that the area of this triangle is 1 over 4. and the area of that triangle is 9 over 4. So 1 over 4 plus 9 over 4, the answer is 5 over 2. Algebraically, it's more difficult if you want to do it with integrals. You need to break it down into two integrals. Why that? Because we don't really know how to integrate absolute values. So we need to look at this function as being made of two lines. The first line, which is decreasing, is negative 2x minus 1, and then the increasing line here is 2x minus 1. And we need to break the integral into two parts, from 0 to 1/2, and then from 1/2 to 2. So the integral of negative 2x minus 1 is this. We integrate from 0 to 1/2. So we plug in 1/2 in that, and then we subtract 0, because negative 0 squared plus 0 is 0. And we do the same for the second half. Here, plug in 2 and plug in 1/2. This is what we get, 0.25 minus 0. And for the second part, 2, I guess this is 2 minus negative 0.25. So it became 2 plus 0.25. And when we put all of this together, of course, we get the same answer as the geometric method. Example 7 is a question where we have to be careful of the sign of the integral. The question is to find the area of the region between y equals 4 minus x squared and the x-axis for x between 0 and 3. With the little sketch I created here, we noticed that part of the area is above the x-axis, part of the area in blue is below the x-axis. So we need to find where the x-intercept is, and we'll have to find each of these two areas independently and then add them up. So what's the area in pink here, purple? It's the integral from 0 to 2, because 2 is the x-intercept, of the function. Here's the integral of the function, 4x minus 1 over 3x cubed. I plug in 2, so it becomes 4 times 2 minus 1/3 times 2 cubed. And I subtract minus when I plug this x equals 0, which obviously yields 0. So the purple area is 16 over 3. What about the blue area? Well, we have to be careful. The integral is going to be negative because the blue surface here is below the axis. So my area is actually negative the integral. The process is exactly the same. The integral is the same. We plug in 2 and 3. I forgot to write them here. And we find that the blue area is 7 over 3. Finally, the area we are looking for is purple plus blue, so the correct answer is 23 over 3. This is the end of the first part of the notes. Either you can go now and listen to the second part, or you can do all the exercises that are in the list at the back of the notes, up and including exercise 45. See you in the second part.